Hello guys, welcome once more to another video in our YouTube channel. So in this video guys, we are going to be looking at the integral of the x on the x. It is weird actually. How can we be integrating the x by the x? So when I posted this question, I had many reactions from people. People were saying that the x is going to cancel, you're going to have the integral of 1 and you cannot do anything again. Some people were saying the integral of 1 is x plus a constant, forgetting to know that you cannot just integrate 1, you need to integrate with respect to something. So guys, at the end of this video, you are going to see how to integrate the x on the x. But before showing how to integrate the x on the x, we are going to go properly into what this video is all about. So we'll be looking at a question that came in the Southwest Regional Mock of Further Mathematics 2022 paper 2, and it was a question on application of integration and the PAPPUS theorem. So I'm just going to display the equation. When we solve the equation, then we conclude the video with integrating the x on the x. Alright, so the equation reads, Roman 1 says that you have x equal to 2a sine squared theta, and then we have to show that the square root of 2a minus x all divided by x is equal to cot theta. That's Roman 1 of the equation. Now Roman 2 says that hence you should show that the area of the finite region bounded by the curve xy squared equal to 4a squared into 2a minus x, the x-axis and the lines x equal to a and x equal to 2a is a squared into pi minus 2. Now we have a statement that says that this area above is now rotated completely about the x-axis. Roman 3 says we should find the volume of the solid of revolution which is obtained, and the last part of the equation is saying we should use the PAPPUS theorem to deduce the distance of the centroid of this area that was rotated from the x-axis, and we should show that it is 2a into 2 ln 2 minus 1 on pi minus 2. Alright guys, so we are going to begin with the first part of the equation, which is asking us to show that if x is equal to 2a sine squared theta, then the square root of 2a minus x all on x is equal to cot theta. So we are going to begin with what we know, which is x equal to 2a sine squared theta. Since we need cot theta and we know cot theta is cos theta on sine theta, we start by looking for sine squared theta, then we see what we are going to do later. So sine squared theta, we can obtain it by dividing both sides by 2a. Our a cannot be 0, so sine squared theta will give us x over 2a. But if we need cot theta, right, then we need to begin with cot squared theta because we have information about sine squared theta. So cot squared theta is cos squared theta on sine squared theta, and we know the identity of cos squared theta as 1 minus sine squared theta. But since we know what sine squared theta is, it is x on a, we just replace, we look for the LCM and we simplify. We get that our cot squared theta is 2a minus x all divided by x. Now we do an assumption that theta is an acute angle, meaning that it is positive. So automatically the cotangent of theta will be positive. So we just take the positive square root of 2a minus x all divided by x. Actually, cot theta will give us plus or minus, but since we are assuming that theta is an acute angle, then we just take the positive square root. So we are proving that. Now the B part is asking us to show that the area of the finite region bounded by the curve xy squared equal to 4a squared into 2a minus x, the x-axis is simply the line y equal to 0, and the other lines x equal to a and x equal to 2a is equal to this a squared into pi minus 2 square units. Alright, so we know the formulas to find the area bounded, the area of a region bounded by lines. So in this case, we just integrate from the bounding values of x, meaning from a to 2a of our y dx, where y is a function. But we don't have y, so we need to look for it, right? So we begin with the equation that x and y satisfies. That's for the curve. The equation is xy squared equal to 4a squared into 2a minus x. We can divide all through by x, and then now we take the square root on both sides. When we divide all through by x, we take the square root on both sides, we simplify, we just take the positive square root. Alright, so we are going to have this left hand side is supposed to be y and not y squared, so sorry for the error. So the left hand side will give us y and the right hand side will give us 2a, the square root of 2a minus x all divided by x. So our integral becomes the integral from a to 2a of y, where y is 2a, the square root of 2a minus x all divided by x. Now we go back to our substitution. We need to use a trigonometry substitution. In this case, What is the substitution? It is x equal to 2a sine square theta. Why are we using this? We are using this because in our integral we can find what we proved in the first part of the equation. We can find the square root of 2a minus x all divided by x, and we proved that it was cot theta. So we are going to dwell with this substitution. So taking x to be 2a sine square theta, right? Then we can differentiate both sides to get the x to be equal to 2a into 2 sine theta cos theta d theta, which will result to 4a sine theta cos theta. Now remember that we are changing variable from x to theta, so also need to look for theta. So we begin by looking for sine theta. Our sine theta, remember theta is an acute angle, so if you look here, you see sine square theta is x on a, so sine theta is the positive square root of x on a because theta is an acute angle, meaning it is positive. Alright, lies between 0 and 90, and in the interval 0 to 90 the sine function is positive and increasing as well. Alright, so sine theta equal to the square root of x on a. We can take sine inverse on both sides, and you're going to get theta to the sine inverse of the square root of x on a. Now we need to change our bounds because we are changing the variable, so the bounds also need to change. X begins from a and ends at 2a. We need to look for where theta begins and where theta ends. Theta will begin from when x is a. When x is a, you have theta to the sine inverse of a divided by 2a. That's sine inverse of the square root of 1 on 2, and that is 45 degrees. That's pi on 4. When theta is 2a, we get when x is 2a, we get theta to the sine inverse of the square root of 2a on 2a will give you sine inverse of 1, which is 90 degrees as pi on 2. So our area becomes, now our 2a is a constant, but it's going to multiply with the 4a here, right? Because that is the x. So it multiplies with the 4a to give us 8a squared. Now the integral from pi on 4 to pi on 2, because those are our new limits of integration. Now in the place of the square root of all of this quantity, I replace it with cot theta because I proved in question 1 that it was cot theta. Now in the place of the x, I replace it with my sine theta cos theta d theta because I already multiplied the 2a with the 4a here to give me 8a squared. So now I simplify cot theta to give me cos theta on sine theta. We now see sine theta is common in both numerators, so they cancel out. We get the area to be the integral to be 8a squared, the integral from pi on 4 to pi on 2 of cos squared theta d theta. But we need to transform cos squared theta d theta because we cannot integrate it normally, so we transform it into cos 2 theta. So by the identity, our cos squared theta is cos 2 theta plus 1 all divided by 2. The 2 can go outside and meet 8 to give you 8a squared on 2, which is 4a squared. Now the integral from pi on 4 to pi on 2 of cos 2 theta plus 1, or you were integrating with respect to theta. Now we just integrate separately. When we integrate cos 2 theta, we get a half sine 2 theta. When we integrate 1, we get theta because we're integrating with respect to theta. Now from pi on 4 to pi on 2, we fit the upper limit and we fit the lower limit and subtract. We simplify, we get our proof that the area bounded by our curve and the lines x equal to a, the x-axis and the line x equal to 2a is given by a squared into pi on 2 square units. Alright, the last but not least part of the equation, Roman 3, then we move on to Roman 4. So Roman 3, we are supposed to find the volume of the solid of revolution obtained when that area is completely rotated about the x-axis. Now these are the useful informations that we had in the previous slide. So we are going to begin with the formula of volume of revolution. The volume is given by pi times the integral from x equal to a to x equal to 2a, because those are our bounding axes. So x equal to a to x equal to 2a of y squared dx. But what is y squared? What is y squared? Our y squared is 4a squared into 2a minus x all divided by x. So our volume becomes the integral. It becomes pi times the integral from a to 2a of 4a squared into 2a minus x all divided by x. We can pull out the 4a squared outside, it multiplies with a pi, then we integrate this. We can separate the x, that's we take 2a on x minus x on x, properties of the LCM. Alright, so integrating, we can now separate the integrals. Integration is commutative over subtraction, and associative over subtraction, sorry. So when we integrate 2a on x with respect to x, we get 2a ln x. I'm taking just ln, I'm not putting absolute value of x because I'm in the positive region already, since a is a positive constant. So the interval a to 2a is really positive, so I just allow the x without the absolute value. Minus, integrating x dx, we get x now from a to 2a. We fit in our limits of integration. Here is the upper bound. We fit x equal to 2a, minus we fit x equal to a. We bring like terms together, we simplify, and we get our volume to be 4a squared pi into 2a ln 2 minus a cubic units. Now the last part of the equation, which is very interesting, is now using the theorem of PAPPUS to deduce that the distance of the centroid of this area from the x-axis is given by these meters. So I'm just going to give you guys a little representation. If I have a curve, right, and I rotate the curve completely about the x-axis, then the center of mass or the center of gravity of this curve is located at that point. We can call the point G. What we are supposed to find here is what the distance of the center of mass from the x-axis. You can call it y bar. Now PAPPUS theorem says that the volume of revolution is equal to the area times that coordinate, then times the angle of revolution. But since we rotated completely about the x-axis, then we rotated about 2 pi radians, so our angle is 2 pi. So the volume becomes 2 pi times the area times the distance of the center of mass of our rotated area from the x-axis. All right, we already have all these informations in the previous questions, in the previous subparts that we're finding. We found the area and we found the volume. So we can get the y coordinate of the centroid. It's simply the volume divided by 2 pi a. But what is our volume? It is 4a squared times pi into 2a ln 2 minus a, and our area is given by this a squared into pi minus 2. Now here we have 4a squared pi over here is 2a squared pi. We just get 2 into now we have 2a ln 2 minus a, all divided by pi minus 2. We can factor out the a from here, and finally we get that proof, which is 2a into 2 ln 2 minus 1, all divided by pi minus 2. Alright guys, so that is it for the video, and for the next video we are going to be looking at the reduction formula. It is still from the Southwest mock. This was the second part of this question because this was actually question 6. What we just saw was part A that was divided into 4 subparts, and now this is the second part of the equation. So in the next video we are going to be solving this second part of the equation. Endeavor to subscribe to the channel, like the video. If you want to get to me, maybe if you have some difficulties, you can get to me via WhatsApp. If you are integrating dx on dx, we cannot cancel out the dx. It's not possible because if we cancel out the dx, the integral becomes void. We'll be integrating 1, but we cannot integrate just 1. We need to integrate with respect to a variable. That's why the dx is supposed to be there in the numerator. So what we are going to see is we are going to we are going to remove the d in the denominator. So we actually see that what is this d in the denominator is a constant because we cannot, the x in the numerator tells us that we are integrating with respect to x, but the dx in the denominator, this d here is a constant, so we pull it out. You are not going to be told that it's a constant, but since we know we cannot cancel out the x and the x must be in the numerator, then automatically the only thing to do is that we factor out the d from the denominator and we call it a constant. The two d's, they are d's, but they have different definitions. One is for dx, a variable change, and the other is a constant. Okay, now when we integrate dx on x, we get ln of the absolute value of x plus a constant. I can call that constant Maffa. So Maffa is a constant. Alright guys, so that was it for the video. Make sure you like the video, like I said, subscribe to the channel if you're just joining us, and thank you for watching.